results, and finally the conclusion. And here's the problem. It wants us to find the condition under which dry spaghetti falling on a hard fork does not break. So we want to find the critical condition that the spaghetti will not break. Okay, our preliminary observation tells us that spaghetti is actually very hard to break. So when we tested it, less than 1/4 break when we dropped it from 4 meters high. So it is very difficult. And there is also excessive deform before breaking of each spaghetti, and there's a wave actually forming in the spaghetti, and this bending part actually can make the spaghetti to break. And sometimes spaghetti will break into uneven pieces. So this is a preliminary observation. And now this is the bending observation done by other researchers. So as we can see, this person releases the one end of the spaghetti, a wave will travel through the spaghetti, and it will form a peak up here, and it will eventually break off. And now this is our spaghetti, if you can see it, and this is an example of a broken spaghetti. So as it falls, it attaches and it breaks. And we have demonstrations of unbroken spaghettis too. So this one, although it deforms, it does not break. Okay, so it just wiggles around. Now, our observation of those two videos is that the end point, which is of the spaghetti that is not in contact with the floor, moves at almost a constant speed. So until the wave reaches it. So let's set the observer moving at the same velocity as the initial spaghetti, so we can observe the wave even better. Okay, so this is how it goes. So first, this part is in contact with the table, and a bent wave will be traveling along the spaghetti. See this bent wave, and finally at the end, it will eventually amplifies, and eventually when it reaches the terminal, and it will go over a specific curvature, and it will break off. So that's how spaghetti breaks. So we also find out that when the contact angle, which is the angle between the horizontal and the spaghetti, when the contact angle is small, the wave we can see a traveling wave like we have seen and break off at the end. However, if it was a large contact angle, we can't see the wave, but we'll just see this spaghetti. However, the final state of each of the spaghetti all look like this. Okay, so let's think of the spaghetti as a piece of landing paper. So a paper lands, and it will eventually bend and break at some point if it was a spaghetti. So what happens is that when the spaghetti falls onto the ground, it will tend to bend. However, because it has elasticity, so it will tend to push itself back. So if the greater force was applied by the floor, it will tend to bend a lot. However, if the force applied by the floor is too small, that the spaghetti will just come back to its original position due to its elasticity, the spaghetti won't break. So we know that there would probably be a specific force that will break the spaghetti. So onto our calculations. Let's set our time from touching to collision of the other endpoint T1, which is L sine theta over V. And the change of momentum of the spaghetti is mv, because we can see that the spaghetti basically doesn't bounce very much. And the basic buffering time, because of the bending, we set it at T0. This is just a correction. The time during collision would be T1 plus T0. So we can calculate the average force via delta P over delta T. So if this average force, let's say if it's greater than the value, say, because formerly we say that there is a critical force. So if it's greater than a critical the spaghetti would break. So our calculation is that if this this is theta c is a critical angle, is related. The critical angle that the spaghetti will break is related to the velocity of the spaghetti. So now this is our equipment and materials, and these are the possible parameters of hitting the floor: velocity, collision angle, length, and angular velocity of the spaghetti. And let's see what effects does the collision angle has. So first, if the spaghetti is under 20 degrees, little amount of energy could be stored in its elastic energy. However, if the angle was higher, a lot of energy will be stored, and as we have said, it'll just release its energy by coming back up straight. So it will be hard for the spaghetti to break. Okay, so our first experiment, we're going to determine the critical condition of the breaking spaghetti. And so in our equation, we said that every velocity will probably lead to a critical angle. That is, yes, a critical angle. So we're going to find that out. And how we determine the velocity is that we determine it by height using the equation. And so how come we can just use the height? Because we have estimated that with a high-speed camera that the air drag is actually negligible because of the small difference it has done to the spaghetti. And so because, as we have said, the original spaghetti was too hard to break, so we processed it with different kinds, but the first two kinds of processing wasn't good because it changes a lot of the spaghetti's texture. So what we did is we bake it to make it easier to break and easier for us to observe. So the difference, what the baking does to the spaghetti is that it changes the maximum force required to bend the spaghetti. So this is our dropping apparatus. We tilt this and we release the spaghetti from here, and we can record the falling of the spaghetti with a high-speed camera, and we can determine the angle of the falling spaghetti. And now we want to calculate the critical angle. This is how we calculate critical angle, because we know that higher, as the angle increases, the spaghetti will be harder to break. So we have derived a lot of experimental points. These are the theta, that the angle that the spaghetti did break, and these are those that did not break. So we take the the two maximum of the breaking angle and the two minimum of the non-breaking angle, and we find out, and we average them together to get our critical angle. So this is how we get our critical angle. So our experimental results shows that as the velocity here increases, this is the velocity, and that's the critical angle, as we can see. And so we know from this graph that under these conditions, the spaghetti won't break. That is low velocity and high angle of contact. And from this graph, we can also determine the T0 that we have previously assumed, and we can obtain it from this point. Okay, and to verify our equation with the theory that we have derived, we plot the theoretical amount with the actual amount, and we find out that it is a line that basically passes through the origin. Now, in experiment 2, we try different length and see how different length will affect this phenomenon. And we found out that as the length increases, the critical angle theta c will also increase. That is, when the length increases, the spaghetti will be easier to break. So from this graph, we can basically get that basically if this length is smaller than a length 7.4, the spaghetti won't break. So why does such minimum length exist? From our equation, we can set this m, the mass of the spaghetti, to be its density times the length. And as we can see here, if this value is greater than the velocity, and so this part will become negative. And what happens is that when this part becomes negative, the sine theta c doesn't occur. So that is the reason why if L is smaller than the value, the spaghetti won't break. So quantitatively, spaghetti won't break under the condition that when no velocity, large angle, and short length. And quantitatively, combining all the results that we have gotten, spaghetti won't break when sine theta is greater than 1.32 times the velocity and times the velocity minus the value. And thank you. This is all of our presentation.
Okay, I have several questions to the reporter. First of all, as I understand in your presentation, you considered the way of breaking of spaghetti if the end which hit the ground does not move.
The end.
Well, if spaghetti falls like this end hits the ground and it doesn't move, and everything further is moving, yes?
Yeah, basically it doesn't move very much.
Okay, thank you. Also, question. When you are measuring the critical angle, as I understood, you've made just, you are measuring it just from 4 measurements. Do you think this is enough and it won't make a big error occurring?
No, we actually have measured a lot, but we have to choose, we have to find
the crossing area, the crossing zone of
the crossing zone between breaking and non-breaking. Yeah.
And how much spaghetti have you been throwing for one experiment?
Oh, like tens and hundreds.
Okay, thank you. Also, you mentioned in your presentation that sometimes spaghetti breaks into uneven pieces. Just wondering, have you tried to make some research on why does it happen and what can affect this effect?
Yeah, I believe that this is going to be a long question, so maybe we could discuss it later. Yeah.
Thank you. Also, when you are calculating the critical force, you are mentioning the value T0. Where does it come from? Is it theoretical or experimental?
It's experimental.
Okay, thank you. Also, can I take a closer look at your experimental setup? How does it release spaghetti?
So first we set the spaghetti on this apparatus and we just turn this apparatus and it'll just drop down.
Okay, and angle you can put an angle on which you will drop, yes?
Yeah, I can move these two parts and it'll change the angle.
Thank you for your answers.